Good morning. Welcome to our seminars. It's a pleasure to introduce Dr. Marcel Popescu. Marcel obtained his PhD in 2012 at the Polytechnical University of Bucharest and the Paris Observatoire. He's now a researcher at the Astronomical Institute of the Romanian Academy, an associate researcher of the Observatoire de Paris. He spent 3 months with us last year in the Tricontinental Campus program for scientific talents, and he's gonna present work we are doing on near infrared colors derived of observed minor planet during the VISTA VHS survey. So thanks, Marcel, for that.
Hello. My domain of study is planetary science. The holy grail of the planetary science is to understand the formation, the evolution, and the structure of the solar system. In this context, asteroids, minor planets, small bodies of the solar system, represent a particular interest since they are the building blocks of a planet. So understanding their physical properties and their dynamics can bring us new clues about our solar system. In this context, using the data of the survey, of the VISTA survey, we want to map all the colors of the minor planets imaged by the VISTA survey. So we split our work in several objectives. We want to find all known solar system objects with apparent magnitude V brighter than 21. We want to retrieve their measurements from the catalogs, from the VISTA data. We want to combine this data with complementary data obtained by other surveys like WISE, like Sloan Digital Sky Survey, to create a map of the small bodies of the solar system, of the physical properties of the small bodies of the solar systems. A byproduct of our work will be, of course, the accurate astrometry of all the bodies found in this imaged by the survey. So, as an introductory point, why to study boulders, space boulders, since we have our own boulders here on Earth? Well, there are several reasons. First is the scientific reason, then is the practical reason. The scientific reason was very well put it down by Antonella Barucci in Marco Polo Yellow Book, and the scientific points said that by studying minor planets we can answer to several questions such as what are the processes occurring in the early solar system, what are the physical properties of the building blocks of the terrestrial planets, do minor planets contain pre-solar material yet unknown in meteorite samples, and how can asteroids shed light on the origin of molecules necessary for life. To investigate these points, the space exploration is undergoing all over the world. Several missions are already gone to minor planets, several are still in preparation, like OSIRIS-REx, Hayabusa 2. Of course, before sending a mission to these bodies, we need to investigate them as much as possible using the telescopes from here, from the Earth, and to have a clear information about them. After that is the practical reason. We study these bodies maybe because we want to be heroes, we want to save the world, why not? And space situational awareness, avoiding events such as Chelyabinsk meteorites, and after that, even still it's in infancy or sounds like somehow as a SEFE, mining minerals from minor planets for future exploration of the solar system. Well, what are these small bodies of the solar system? Their definition is given by the exclusion. They are orbiting the sun and they are not a planet. So we call them small bodies of the solar system. We call them minor planets, asteroids, which includes asteroids, comets. 20 years ago, we know about 10,000 such objects. Now we know 700,000 objects. Most of them are orbiting between the orbit of Mars and of Jupiter, and are called main belt objects. Others come in the inner part of the solar system, and they are near Earth objects, about 13,000 known until now. Well, even we know these numbers are quite huge. Physical information about them, it's quite sparse. We have the albedos of about 100,000 asteroid of WISE, several 10,000 of visible color from Sloan Digital Sky Survey, and that's all with the big numbers. Spectral data we have only for 3,000, mainly in the visible part, gracefully to the two surveys, Bass and Binzel in 1995 and 2002, and Daniela Lazaro in 2004. And we have some near-infrared data, mostly of near-Earth asteroids, because they are somehow very interested being in the inner part. And from here I need to remember the survey of MIT minus and of Julia with several tens. Now, we have some data in the visible from the Sloan Digital Sky Survey. We have the albedos from WISE. We need near-infrared data. And here we have a treasure from the VISTA-survey, which will provide us a very large data set of data. VISTA, it's a 4-meter class telescope. It is located in isoparanal here. It's dedicated to the Wide Field Survey telescope and wants to image the entire southern hemisphere. They expect that the data will be 4 magnitudes deeper than the previous surveys taken by Tumas and Dennis. It has a camera with this field of view, 1.3 of 1 degrees, here compared with the moon. It comprises 16 detectors, a bit sparse. So in order to cover a whole field of view, 6 images need to be combined. And each area is covered at least 2 times. The blue one, the red one 3 times, and so on. So the most important survey of VISTA telescope is the VHS, which covered this area of the sky. The number of images taken in different filters depend on the sub-survey. It has 3 filters, YJH for the Atlas sub-survey. Dark energy survey will take images in JH and KS, while GPS will take images just in J and KS filter. So how we'll find our minor planets in the images of VISTA? Well, compared with the star, minor planets appearing as moving objects. And saying moving, this means moving. 0.3 arc-second minute for a main belt object, about around 2 arc-second minutes for a near Earth, but this can vary a lot. And the icy worlds beyond the trans-Neptunian orbit moves a bit slower. Here it's an image of an asteroid moving in a field of stars. We can predict its position at any moment by knowing its orbital properties. the prediction of a position of such object depends a lot of the uncertainty which we have for the orbital elements. If the orbital elements are well known, we find very easily the object. Otherwise, the object can be anywhere in the field. Because they appear as moving objects, when looking for this object, we deal with several issues. Of course, first one is the uncertainty. The object cannot be at the position we expect it to be. The second one, because it's moving, it can overlap with a background source. The third one, because it moves, if we take long exposure, the object can appear as a trail. Or if we combine exposure obtained at a sparse moment in times, we can, though our object can appear as double-lobed or as a multiple-lobed. Here, because I like these images of the comet La Sagra, observed by the La Sagra people from here in Spain. Here is the comet La Sagra in the VISTA VHS hemisphere survey that I found it, just to exemplify. So, looking on all the images of VISTA survey, we need a strong algorithm to deal with this issue and to be sure that what we are detecting is correct. We start with observational logs, what VISTA observed. After that, we predict which of the minor planets can be in the survey. We try to retrieve their detection. Are our prediction correct? Then we need to do a filtering of the obtained data. And we need to combine all this data, which represent detection and measurement of individual objects, put them all together to obtain good information, useful information for us to characterize. We may average some of the data, we can obtain colors, we can obtain spectrophotometry. What they observed until now. So the data we worked covered about 40% of what they proposed as survey. The area of the sky covered is shown here. Most of the images are obtained in J and K filters, but we have also images in Y filter, which I will show is very important for us, and as well in H filter. This area of the sky, it's about 8,000 square degrees in any band, and comprise about 86 images. 8,600 images, sorry. First, we need to predict the observation. We need to know which of the 700,000 objects are presented in each field. For that, we need to compute their accurate position in the limit of the uncertainties. For this, we used an ephemerid service, Skyboot, which allows to predict all the solar system objects present in an image. And we predict that in the VISTA images we will have about 68,000 objects, and 62,000 objects will have uncertainties lower than 10 arc seconds. For the other 6,000 images, which can bring a lot of astrometric information, we need to employ separate algorithms, because they can be, in fact, they could have their position very different from what we predict. Of course, we cannot go to retrieve the images of 62,000 objects, because it will be a bit crazy. Instead of that, the guys of VISTA prepare all the things for us. They cataloged all the sources in the in each images, and make all the measurements in all and all the information available online in a catalog called detection catalog. So we considering these detections, we go in the catalog and look which of these objects can be found in the images. We retrieved 300,000 detection corresponding to 47 objects. This is correct since we go to fainter magnitudes, so some of them may not be detected due to the fact that they are too faint. As well, we cover the larger area for prediction to take into account the uncertainties. Of course, if I'm working with table and I don't see any images, you will not trust me, say that this data cannot be true. So we need somehow to validate, to bring arguments to convince that what we obtained is correct. We removed measurement marked as directed. This information is provided. Then we did a comparison with star catalog to remove those that overlap with the background sources. After that, we compared the coordinates of the observed object with what we computed and developed an algorithm to remove those that are outside the astrometric precision provided by VISTA, which is about 0.3 arc seconds. Here is the data that the guys of VISTA provided. As a comparison to see how well this validation job was done, we compared the magnitudes of the objects that overlap a background star, so their magnitude is influenced by the background source, with what we obtained, predicted minus observed. So we see that the predictions are quite well within one magnitude between between the magnitude in V and the predicted magnitude and the observed magnitude in J, compared with those that overlap, which are quite spread. Regarding the signal to noise ratio, we retrieved the photometry in the 4 filters using an 1 arc second aperture radius. We stopped to V magnitude 21, and our choice is correct since we will not have a photometric magnitude error lower than 0.1 above in Y filter and A filter. Maybe we can find some object in the J filter which can be good for astrometry, and the limit is about 20 in K. As you can see, their detection is saturated to magnitude error about to 0.4. Well, we have the measurement catalogs. We retrieve these are all our detections. Now we need to combine them to obtain useful information. So comparing minor planets' magnitudes observed at different epochs, it's difficult since it needs to take into account that the brightness vary with the light curve variation, to the shape variation of the object, and to its position in Earth-Sun object, in the Earth-Sun object geometry, varying with the heliocentric distance. So we need to make several assumptions to combine different measurements. We can neglect upper end magnitude to the variation of the heliocentric distance for a single night. We can neglect light curve variation for intervals less than 15 minutes. The second one is quite hard to achieve, but if we look from the statistical point of view in the frequency diameter rotation of each asteroid, we can see that considering that most of our objects are big objects, we can stop to about 15 minutes will imply an error magnitude of about less than 10% of its light curve variation. Of course, the imaging strategy was good for us because they take J filter, then H filter, then K filter, which allows us to be within these 15 minutes. Another stuff to assume, we need to assume that asteroid surface is compositionally homogeneous, so we can compare colors obtained at different epochs. So, for combining all this data, we averaged the measurements in 15 minutes. We select the magnitudes for spectral photometry such that the interval between the observation to be minim. We obtain colors, difference between the magnitudes obtained in different filters, with the closest in time detections. So, as you may see here, the Y minus J and H minus K were obtained in 5 minutes, 10 minutes for Y minus K and J minus H, and about 20 for Y minus H, for which we will not use it. So, this is what we obtained. These are all our objects for which we get data spread in semi-major axis and eccentricity. We gather all this data in 3 separate catalogs: detection catalogs, magnitude catalogs for spectrophotometry, and colors catalog. They are in separate catalogs because their process for obtaining it's a bit different, such that to be optimally in time. The harvest. We obtained about 3,000 objects with magnitude error below 0.1 in IJHK filter, and this is about 2 times more than the last data release of TUMAS with 40% of the VISTA VHS survey considered until now. Showing, of course, because they took images in different filters, we obtained colors. The number of colors obtained for each object can be different. If we compare with what was published for TUMAS, we can see here that we are about 10 times more compared with the early publishing, but they updated this stuff and it's about 2 times. How reliable? It's our photometry. We have objects observed in a separate night. So we cannot compare directly the magnitude, but we can compare the colors, which is correct in the assumption of surface homogeneous surface. So if we compare the photometric error obtained with the spread of the colors measured in different nights, we can see how reliable is the photometric error. And this is true true in the definition of the standard deviation. About 70% which have photometric error lower than 0.1 measured photometric error have a spread from multiple nights in colors lower than 0.1. This is true for all the colors. Of course, we have some common objects measured also in TUMAS, and we can compare these objects, the data obtained by TUMAS, with our own data. We need to apply some equation between their filters and the filters used by VISTA, and as you may see, the distribution is quite well centered of 0, with some outliers beyond 0.2, which stays also in the definition. We are doing statistical work, and our data stays well in the statistics, in the standard deviation statistics. So, what to do with these colors? We have colors in the 0.8 to 2.5 microns. In this region, we are dealing with what is reflected by the asteroids. If we put in an equation the flux that we receive as a function of lambda. It's a combination of the reflected sunlight of the asteroid with the thermal emission of the asteroid, and everything is modulated by the atmosphere and the instrument. We are interested only in the characteristics of the asteroids. So for this, we can neglect for most of the objects. This is valid for all the main belts, the thermal emission in the 0.4 to 0.5 microns. For some particular cases, we can have of near-Earth asteroids that come very close in the inner part of the solar system. We can have some thermal emission, but we neglect it. We can remove the solar features using the analog G2V stars. What we expect to find? The basis for our study is the data obtained in the laboratory on the meteorite spectra. We know that we have most of the most important materials found in the meteorite spectra, pyroxene, olivine, iron, nickel, have features in the 0.4 to 0.5. In particular, pyroxene with a band at 2 microns, and olivine with a band at 1 micron. No feature for iron, nickel. In order to obtain this data, spectra of asteroids were observed since 50 years ago. Accurate spectra can be used to compute the mineralogy. Since the beginning, they observed that these spectra are quite similar, so a statistic can be made of them, and several types can be obtained. Initially, they found that we have stony asteroids, silicate types, carbonaceous chondrites, metallic asteroids. As well, we have some asteroids characterized by a very red and dark spectrum. The last, so gathering a sufficient set of data allows to derive these types. The last type, which consider the data from the visible to the near infrared, is called Base-de-Meaux taxonomy, and splits the possible the model of the spectra of the asteroids in several types. We have the C complex, carbonaceous chondrite. We have the X complex, in which we need to differentiate between metallic and enstatite and maybe some carbonaceous chondrite based on the albedo. Then we have the silicate complex with some extreme end members, the basaltic asteroid, Vesta type. So, our colors obtained from VISTA, Y, J, H, and KS filters are exactly where we need. We are around a band of 1 micron on the slope between the minimum and the maximum of the first band with the J filter. With the H filter we have on the maximum, and on the 2 micron band we have the KS filters. This is for a asteroid spectrum very similar with ordinary chondrite meteorites. This is for a vestoid type, basaltic asteroid, and for a metallic one. So, using only these colors, we can differentiate between different taxonomic type, and we can infer their composition. The early work on the 2-mass data showed that we can barely differentiate between S silicate type and C types asteroids, olivine rich, well separated, using only J, A, and K filter. if we put our data with what already is known in the literature, we see that the separation is not so clearly made in this context, and it's hard to distinguish. This is easily shown if we consider those taxonomic types and the uncertainty in the J minus K, H minus K filters, and we can see that even the model it's separated, the uncertainties overlap very well. We may have also V types quite well separated vestoid types, and of course the olivine rich. But the rest, the C-type carbonaceous chondrite, which are the primitives one, overlap with the silicates. B-types overlap with the S-types, and it's hard to distinguish between them. But here comes into play the Y filter, which get the data around 1 micron. For the Y filter, allows to separate very well between the silicate types as carbonaceous chondrite and vestoids. Comparing this graph with the existing graph in the literature, we have carbonaceous chondrite, we have silicate types. These are known taxonomic classes based on the visible spectra. So the intruder may be in fact not well classified. If we do the plot with all the signal to noise ratio better than 30, we can see the great divide quite well here. We can even separate between different C types. The vestoids, of course, are a separate case, and we can easily distinguish them. This can be quite well seen in the, even if we consider a signal to noise ratio better than 10, which is very good, because we have a lot of data in this region. Of course, we can do a lot of combination, having 6 colors, and look which distance allows to differentiate better a specific class. A particular one can be also Y minus J versus Y minus K, a small mistake here, which allows also to separate between silicates and the C types, but also allows the B types. B types come for blue and are Pallas-like spectra. Comparing the data with what is known in the literature, and a particular and very interesting case is the B type. If we put the typical spectrum of Baz-de-Meo taxonomy, the standard spectrum, the objects should be here. The B-type spectra observed by the visible surveys, in fact, are here. And this can be explained by their feature in the near infrared. As shown by Julia de Leon in 2012, the B types vary very significantly in the near infrared part. So basically we are looking here only for this type. But these graphs allows us to differentiate these different continuums. Another part, well separated apart, are the V types or Vesta family asteroids. Well, they are occupied a very separate region. And if we plot the VESTA type, the VESTA family asteroids, we may see that most of them are here. We may have some intruders in the silicate and the C types. The VESTA family is defined based on its orbital parameters. And if we plot it in the semi-major axis and eccentricity, the known V-types, we may see that we can find the V-types asteroid unexpectedly far outside of the VESTA family. For example, this one or this one. Challenging what is known until present, that the VESTA is the only source for the V-type asteroids and also for the Howardite-Euclid Diogenite meteorites. So, how accurate is this data that we obtained? We have in the outer main belt of V-type asteroids. We confirm it using the Isaac Newton telescope. And obtained the visible spectrum, and with the TNG, the near-infrared spectrum. The data show that it's clearly a V-type. We used also Isaac Newton telescope to find other V-types and confirmed them, so it's correct. So, last point, how we can compare the photometry data or colors with the spectral data. We've shown here several examples that the matching is very good. The two different points come from different methods of obtaining G2V stars, for which we need to subtract their features. So, here it's the conclusion slide. Basically, we obtained a lot of measurements, and now we are start to challenge what is known about the physical composition of minor planets. Our science, it's just based on this data, is just as the beginning, because we need to interpret this data. We can characterize the families of different asteroids. We can combine this data with the data obtained in visible and in infrared to have the whole spectral interval to discuss their properties. In particular, we can also see different populations from different regions and see how our data match with what is known about the current models of the solar system formation and evolution. Thank you.
Questions?
Hi. You have mainly spoken about the asteroids, but I would like to know how many trans-Neptunian objects have you detected in the survey?
About tens.
About tens or 10?
10.
Okay, thanks.
10, maybe 20. Not too many because they are faint. And also they move very slow. We can detect very well objects that move relatively fast.
More questions? I have one. I mean, you need to realize that I come from a completely different field, so maybe my question is very naive. I'm looking at the work you're doing, trying to classify the different objects based on these infrared colors, and of course the level of degeneracy is huge, right? So have you considered using, because there are a few surveys, at least in the for galaxies, running where we have many narrowband filters across the entire spectrum, from the optical to the infrared. Will that give you a better leverage to distinguish between all these families? I'm thinking about shards, for instance. We use it for galaxies because we want to get the spectral energy distribution for the entire galaxies. This is, I think, 40 filters, narrowband filters. So it seems to me that this is probably a somewhat more efficient way than trying to do it with just 3 or 4 colors, which is what you see there.
We are dealing with the solid bodies, so we have bands, very large bands, around 1 micron and 2 micron. And these are some typical spectra we expect, so we need to sample exactly.
Yes, but here the difference is done, the wiggles here matter quite a lot. So sampling these wiggles with 4 filters or with 40 makes a difference.
But we are using something that it is already done.
Okay, you see,
Yes.
that's why. Okay, that's why my question was naive. Very good. More questions? No? So before we move to the coffee, which should be sitting outside the cafeteria, let's thank our speaker again.